Okay, so good evening and welcome back to this problem solving session for the NPTEL course Foundation Engineering. So, in the last week, we had solved a few problems regarding lateral earth pressure based on Rankine's theory and as well as Coulomb's theory. So, in this week, we'll basically solve a couple of problems regarding seed pile wall. Okay, so that is another kind of retaining structure, and from this week we started learning about that aspect. But before that, we'll first solve a problem regarding various design checks which are required to ensure a safe and satisfactory performance of a gravity retaining wall. And that problem basically was given in the last class itself as a homework problem. Okay, so we'll start with that and then we'll take a few problems related to seed pile wall and we'll close this session for today. Okay, so before that, so we'll have a quick recap for the topics which we have learned in this week. So firstly, we have seen different design checks for cantilever retaining wall, and it's similar to the gravity retaining wall which we had basically learned in the previous week. Okay, so through an example problem we have basically seen what are the different design checks which we should perform for a cantilever retaining wall. Okay, and we'll see in details through one numerical example problem in this week as well. Next, what should be the base width to be provided for no tension condition at the base of retaining wall? That aspect also we have learned from this week. And next, minimization of water effect in the backfill. So different by different techniques we can minimize the water effect in the backfill because it's uh, it's basically not uh, recommended, or it's basically an undesirable condition for geotechnical engineers. Okay, so water effect in the backfill, so therefore we should always try to minimize the water effect through these techniques. We pull perforated pipe, filter, and so on. And lastly, some remedial measures to sliding failure of a retaining wall, and it can be done in by providing a shear key at the base of the wall. Okay, so these two pictures basically uh, depict this point number 3 and point number 4. So this figure, this depicts about the minimization of water effect in the backfill through weave, and this figure remedial talks about remedial measure to sliding failure of retaining wall. Now in the next part of this week, we started learning about sheet pile wall as I just mentioned, and there can be two types of sheet pile walls. The first one is cantilever sheet pile wall and the next one is anchored sheet pile wall. So this figure 1, this depicts the schematic diagram for cantilever sheet pile wall, and this figure 2 depicts a schematic diagram for anchored sheet pile wall. Now in this week we only have learned about cantilever sheet pile wall, how to basically determine the net earth pressure diagram on a cantilever sheet pile wall for both purely cohesionless and purely cohesive soil. Okay, and subsequently how to determine the depth of the wall. Now, what are the fundamental differences between the sheet pile wall and retaining wall? So earlier in last week we had learned about retaining wall. So what are the different design checks or how to perform the different design checks. Now in this week we have learned about this sheet pile wall. Now what are the fundamental differences between this retaining wall and sheet pile wall? So the major fundamental difference between this sheet pile wall and the retaining wall is that this retaining wall, this is a rigid wall, so it basically derives the resistance against the earth pressure due to its self weight only. Okay, whereas this sheet pile wall, this is flexible in nature, so it basically derives the resistance from the depth of the wall. Okay, so D. So therefore, in case of sheet pile wall, this depth of the wall, that is depth of embedment below the dredge level, is very higher as compared to the depth of the retaining wall, means in case of rigid retaining wall. So this is one major fundamental difference between the retaining wall and sheet pile wall. So retaining wall, this is a rigid kind of wall, so for that its depth of embedment is less, whereas the sheet pile wall is a flexible type of wall, so therefore we have to basically embed this kind of wall to a higher depth so that it can be safe against the earth pressures which are exerted by the material, backfill material. Okay, so now we'll try to solve this problem 1. So in this problem, a gravity retaining wall made of concrete is designed with the dimensions as shown below. So we have to comment on the design of the wall, given that the unit weight of concrete is 24 kilonewton per meter cube, adhesion factor for the subsoil is 0.9, and the properties of the subsoil it rests on and that of the backfill are listed in the table below. So this is the schematic of the gravity retaining wall. So these are the dimensions. Top width of the wall is 0.3. Okay, all are in meter. So all dimensions are basically given in meter. Then this is the embedment depth, 0.5 plus 0.5, that is 1 meter. This is the height, you can say 4 meter. And this is the base width, 0.65 plus 0.7 plus 0.3 plus 0.7 plus 0.65. So as a whole 3 meter. So these are the backfill properties. Unit weight 20 kilonewton per meter cube. Cohesion is 0. Angle of internal friction is 36 degree. And the wall friction, angle of wall friction is 2/3 of this 5. And these are the subsoil properties, where unit weight is 17 kilonewton per meter cube, cohesion is 15 kPa, phi value is 25 degree, and delta, that is at the base. So here the angle of wall friction is 0.75 times 5. Now last class we had discussed a little bit about the various design checks which we should perform before commenting on the design of the wall. And these design checks are, first of all, we have to determine factor of safety against overturning, whether the wall is safe against overturning or not. And this factor of safety against overturning, we have to check against about the toe of the wall. Okay, so this is the toe and this is the heel. Then factor of safety against sliding. Then thirdly, factor of safety against bearing failure. And finally, check for no tension condition at the base. Now, what are the recommended factor of safety? That also we have seen in the last class. So factor of safety against overturning, it should be in between 1.5 to 2. So these are the this is the desired range. Okay, so 1.5 minimum you have to basically provide. Then sliding 1.5 to 2. Then bearing failure 2.5 to 3. And for no tension condition, that eccentricity we have to check, eccentricity of the applied loading, it should be less than b by 6. Okay, so first we'll start with the calculation of lateral earth pressure. That is, for that we should know the coefficient of active earth pressure. Now, the coefficient of active earth pressure, for this problem, you have to basically employ the Coulomb's theory of earth pressure. Okay, why? Because we are basically considering some wall friction. So it's not zero. So if it is zero, then you can go for the Rankine's theory. However, before implementing the Rankine's theory, there is one check. That check you have to basically fulfill or satisfy. Okay. However, for this problem, since the wall friction is not zero, so there is a non-zero wall friction value. That is the wall backface wall. It's not smooth. It's basically rough. It's not perfectly smooth. It's rough. So you have to go for the Coulomb's theory of earth pressure. Now, as per Coulomb's theory of earth pressure, the active earth pressure will basically act at a height of h by 3. Okay, so this height is basically h by 3, and this is the perpendicular to the wall face. Now, with this perpendicular, your active earth pressure, the resultant pressure will basically act at an angle of delta. Okay, so this is your delta. Sorry, this value is your delta. Now, what is this h? So in this case, the h is basically this total height. The h value is basically 4 plus 0.5 plus 0.5. Okay, or okay, so to create confusion, so here I am writing the total height. It will be 4 plus 0.5 plus 0.5, that means 5 meter. Okay, so the resultant active earth pressure, it will basically act at a height of h by 3 from the base of the wall, but it will act basically at an inclination of delta with the perpendicular to the backfill face. Wall back face. So this is the wall back face, and this is the perpendicular. So this is the perpendicular to the wall back face, and your resultant active earth pressure will act at an angle of delta with this perpendicular to the wall back face. Now, how this delta value we can get? So delta value we can get from this value. So it's basically given in the problem statement itself. So it will be 2/3 of the backfill friction angle value. So backfill friction angle value is your 36 degree. So your delta value would be 2/3 into 36. That means 24 degree. Okay. So here we are calculating 2/3 into 36. That means 24 degree. So this is the value of delta. Now we have got the value of delta. Now what we will do? We'll try to figure out this angle as well. Okay, so this angle, suppose we are introducing a variable called beta. So what is the inclination of this perpendicular to the back face with the horizontal? Now how you can get this value beta? So you can get this value beta in this fashion. So we know the inclination of the back face. Suppose this is your alpha. Now if we know the inclination of this back face as alpha, so this value will also be alpha. Okay, and again this alpha plus beta as a whole will give you 90 degree. So alpha plus beta, it will be 90 degree. Now how we can get the value of alpha? Alpha value, it's very simple. It will be tan inverse this triangle. Please consider this triangle. Okay. So this is the height and this is the base. Now what is the height of this triangle? So height of this triangle is basically 4 plus 0.5. That means 4.5 meter. And what is the base value? The base value is 0.7. So 4.5 divided by 0.7, that will give you the alpha. Okay. So this value would become 81.16 degree. If you calculate, then this value would become 81.16 degree. Okay. So if alpha value is your 81.16 degree, then beta value should be 90 minus 81.16. That means 8.84 degree. So therefore, we have got the total inclination of this PA with respect to the horizontal. So earlier we know the inclination of PA with respect to the perpendicular to this back face. Okay, back face of the wall. Now we got the total inclination, that is delta plus beta, because delta value is your 24 degree and beta value is your 8.84 degree. So if you add these two values, so you can easily figure out what should be the total inclination of this PA with respect to the horizontal. Okay. Why this is important, that we'll see in the subsequent discussion. Okay, now we have got the inclination of this PA with respect to the horizontal. Now how to calculate this PA? So the calculation of PA is very straightforward. So PA, this will be simply half Ka gamma H square, because you will be having a triangular distribution. Okay, a triangular distribution for active earth pressure. Now this value is your K gamma H. The total height is your H. So what is the area of this triangle? Half multiplied by H multiplied by K gamma H. So that means half K gamma H square. So that will basically give you the resultant active earth pressure, which is basically acting on the wall. Okay. Now this K value you have to basically determine based on the Coulomb's theory of earth pressure. And why? We have just now discussed that the wall back face is not perfectly smooth. It's basically rough. So it's having a wall friction angle of 24 degree. So we have to go for the Coulomb's theory of earth pressure. We cannot utilize the Rankine's theory. So Rankine's theory is basically applicable when there will not be any wall friction. So the back face will be purely or totally smooth. Okay, so delta will be 0 in that case. And this is the earth pressure coefficient based on the Coulomb's theory. So to calculate the K value, you should know alpha, you should know phi, and you should know delta and I. So four variables are in this expression: alpha, phi, delta and I. Okay, so here we will summarize. So Ka, this is basically sine square alpha plus phi divided by sine square alpha multiplied by sine alpha minus delta root under 1 plus sine I plus delta sin phi minus psi alpha minus delta and sin alpha plus phi. Okay, so please check this expression whether this is correct or not. Okay, so I have taken this from the lecture material itself. So okay, there will be 1 whole square, so you have to consider this as well, otherwise you will get incorrect answer. Now this k, this is basically a function of alpha phi delta I. What is alpha? Alpha, this is the inclination of the backface. We have calculated this alpha value as 81.16 degree. What is phi? This is the friction angle of the backfill material. So this is 36 degree. What is delta? This is the wall friction. We have also calculated it as 24 degree. And what is I? I, this is the inclination of the backfill surface. Now in this case, since the backfill is basically horizontal, completely horizontal, so I value is 0. So I am summarizing here. Sorry, I have to erase this part, otherwise okay. So I am starting with that Ka. This is the function of phi delta alpha I. And what are the values of this variable? So phi, this is 36 degree provided in the problem statement. Delta calculated as 24 degree. Alpha calculated as 81.16 degree. And I 0. This is the problem geometry. Okay. Now substitute these values in this expression of K. So you can easily basically get the value of K. So K value, I hope this value would be something 0.3. Okay, so can you please substitute these values in this expression and let me know whether you are getting the same value or not. So I am getting the K value as 0.3. So can you please let me know? Okay, so I have cross-checked it twice. So I am getting something nearly above 0.3. Okay, so now we'll calculate this PA value. So PA value, it would be half 0.3 multiplied by the, what is the unit weight of the backfill? 20 kilonewton per meter cube. 20 multiplied by 5 square, because 5 is the total height of the retaining wall. Okay, so please calculate and let me know what should be the value for PA. So it would be 75 kilonewton per meter. Now we have earlier determined the line of action of this PA, and this is basically acting at an angle of delta plus beta with the horizontal. Now this value will come into picture because now PA will be having two components along the horizontal direction and along the vertical direction. So we can resolve this PA along two directions, along the horizontal and vertical directions. Okay, so it will be basically like this. So this will be PAH and this will be PAB. Now what should be the value of PAH and PAB? So PAH, so this will be the cost component of PA. So PA cos delta plus beta, and the vertical will be sine component of the PA, sine delta plus beta. So if you calculate, then this value, so delta is your 24 and beta is your 8.84. Yeah, into 75, so that means 63.01 kilonewton per meter, and PAB, this will be sine so 40.67 kilonewton per meter. Okay. Okay, so we have determined the vertical as well as horizontal component of the resultant active earth pressure, which is acting on the back face of the wall, inclined back face of the wall. Now what we'll do, we'll basically try to determine the resisting force and the driving force involved in this problem, as well as their lever arm from the toe of the wall, because this calculation will help us eventually to determine the overturning moment and the resisting moment calculation. Okay, so therefore we will basically make a table. So this is the component, so this is the component, then this is the force, okay, rather I can write it as I, and this is in kilonewton per meter, and then this will be your lever arm. So lever arm, suppose we are denoting as, we can L bar I from row, okay, and this will be meter, and here mm, this will be kilonewton per meter. Okay, so first we'll consider the resisting moment. So resisting moment, so first we'll consider the resisting part. Okay, now what are the components do you think that will give you the resisting moment? So the weight of the wall, this will basically give the resisting moment. Okay, so it will basically try to resist the driving forces. So there are, so we can basically split this geometry of the gravity retaining wall into 4 components. Suppose this is component 1, this is component 2, this is component 3, this is component 4, because this will make the calculation easier. Okay, now we will basically try to calculate all this area, the area of all these components. So area of all these components will give you the force, and as well as we will calculate the CG of this component from the toe of the wall. Okay, so first therefore we'll calculate 1. So how we can calculate this, how we can therefore, okay, so let me renumber. So 1, 2, 3, 4. So how we can calculate the area of this rectangle 1? So rectangle 1, the area will be simply 0.3. This is the width of the rectangle, and this is the another dimension, na? So 4 plus 0.5. So the area would be 4.5 multiplied by 0.3. So this will basically give you the area. Now we are basically considering unit length in the direction perpendicular to this presentation slide. Okay, so we are basically considering with unit length in the normal, in the direction which is basically normal to this slide of presentation. So therefore this multiplied by 1, so that will give you the basically volume. Now volume multiplied by unit weight. Now what is the unit weight? Since this gravity retaining wall is made of concrete, so unit weight of the concrete is given as 24 kilonewton per meter cube. Okay, so multiplied by 24. So volume multiplied by unit weight, so that will give you the force. Okay, resisting force, that is the weight of that component itself. So what will be the value? So 4.5 into 0.3 into 24, that is 32.4 kilonewton per meter. And where it is acting? It is basically acting at its CG. Now CG is basically at a distance of 0.3 by 2 plus 0.65 plus 0.7 from the toe of the wall. Okay, so please keep in mind that all the lever arm you should calculate from the toe of the wall. So 0.65 plus 0.7 plus 0.3 by 2. So 1.5 meter. Now coming to the second component, that is the triangle basically. So its area will be, first we will calculate the area, then we will multiply it with the density of the material, that is concrete. So 0.7, this is the base width, and the height is 4.5. So half into 0.7 into 4.5 multiplied by 24. So calculate in a similar fashion for all the components. So then the third component will be the same value. Okay, so 24. And finally the fourth component, that is again a rectangle. The dimensions are 0.5 and 3. 0.5 multiplied by 3 multiplied by 24. Okay, so calculate this one by one. So first we will calculate this 2, 3 and 4. So 0.7 multiplied by 4.5, 12, that is 37.8. This is also 37.8 and this is 36. Okay, now what is the lever arm of these two components? So lever arm will be at a distance of 0.65 plus 2/3 of this 0.7. Okay, so 0.65 plus 2/3 of 0.7. If you have any doubt, please let me know. So this is the apex of this triangle 2. So therefore the CG will be at a distance of 2h by 3. Here h is basically your 0.7. So 2 into 0.7 plus 3. So this is from the apex. Now from the toe it will be 0.65 plus 2 into 0.7 by 3. Okay, so 0.65 plus 2 into 0.7 by 3. So therefore 1.12. Now for triangle which is numbered or marked as 3, so it will be 0.65, 0.7, 0.3 plus, so this is this triangle 3, 0.65, 0.7 plus 0.3. Now it will be from the base, so it will be simply 0.7 by 3. So 0.7, right? That means 1.88 meter. And for rectangle 4, it will be simply at the mid of this base dimension. So that means 3 by 2, that means 1.5. Okay. Okay. Now apart from these 4 components, that is the weight of the gravity wall, retaining wall. So this vertical component PAV, so this will also try to resist the driving forces which is basically exerted on the retaining wall. So PAV we have to also include. This is PAV equals to what value we have got? So we have got 40.67. Now what is the lever arm of this PAV? So can you please let me know what is the lever arm of this PAV? So to calculate the lever arm, it's quite tricky. So you have to basically draw up a line in this fashion. Now you have to basically calculate from the toe, above the toe, the lever arm. So this distance will give you the, so this distance will give you the lever arm for PAV. Now how to get this value? So we can get this value in this fashion. First we will determine this value. This value will determine. Okay. So how we can determine this value? So we can easily determine this value from this triangle. Okay. So how to determine this base value from this triangle? So for that we have to first know the h by 3. So h by 3 distance, because at a height of h by 3 this force is basically acting. So h by 3 first we will calculate. From this h by 3 we will basically subtract the width of the base, so we'll get this side, we'll basically get this side. Now once we know this side, so tan of this divided by tan will basically give you the base diameter. Okay, so if I draw the picture here, so this is basically PAV acting. Now this height is your h by 3, this is your 0.5 meter. Okay, now this angle you know, alpha. Now what is this dimension? First we'll calculate this h by 3. So h by 3 is basically 5 by 3, that means 1.67. Now if this is 1.67, now this height should be 1.67 minus 0.5, that means 1.17 meter. Okay, now if this is 1.17 means this height is 1.17. So if this is this height is 1.17, then this will be, because tan alpha is basically 1.17 by this base, so this will be 1.17 divided by tan alpha, and alpha is your 81.16. So 1.17 divided by tan, 81.16, so that will basically give you 0.18 meter. Okay, now 0.18 you are basically getting from this point. So from this point you are basically getting 0.18. Now what you have to do now, you have to basically calculate this lever arm from this toe. So we'll calculate first up to this point. So 0.65 plus 0.7 plus 0.3 plus 0.7, because 0.7 up to this part, then we will basically minus this 0.18 meter. Okay, so 0.65 plus 0.7 plus 0.3 plus 0.7 minus 0.8. So that means 2.17 meter. So in this way we have got all the components, force components, which are basically taking part in the resisting, or which are contributing to the resisting part. Okay, now we'll try to calculate the moment as well. So we'll have to simply multiply 32.4 multiplied by 1.5, so 48.6. So 48.6, then 37.8 multiplied by 1.12, that means 42.3. Then 37.8 multiplied by 1.88, it is 71.1. Then 36 multiplied by 1.5, 54. And finally 40.67 into 2.17, that is 88.3. Okay, so from this table, since there is no space, so we'll basically, okay, we'll here calculate the summation as well. So what is the total contribution? The total contribution is summation of FR and here summation of MR. So sorry, summation of FR, this will be here. Okay. So summation of FR would be 32.4 plus 37.8 plus 37.8 plus 40.67. So that means 148. Okay, I am getting some value 32.4 plus 37.8 plus 37.8 plus 36 plus 40.67, 184.67 we are getting. Okay, so this is also you can write as FV because these are all the vertical forces acting on the wall, including the self weight of the wall. Okay, and what is summation of MR? So it will be 48.6 plus 42.3 plus 71.1 plus 54 plus 88.3. So that is 304.3. 304. Okay, now we have calculated the resisting part. Now we will calculate the driving component. Okay, or overturning component. Now, what is the overturning component here? So only the PA, the horizontal component of this PA. So it will basically try to overturn this retaining wall about the toe. Now the horizontal component of this PA we know, so that is basically 63.01 kilonewton per meter. Now what is the lever arm of this PA? So the lever arm of this PA, sorry, not PA, PAH. So the lever arm is basically H by 3. Okay, so this is the lever arm. So therefore the overturning moment MO, so this will be PAH multiplied by H by 3. So PAH is basically 63.01 multiplied by 5 divided by 3. 63.01 5. So 105.02 I am getting. Okay. Okay. Now we know the overturning moment, we know the resisting moment. Now what we will do, we will basically try to locate the location where the resultant of these forces will basically act. So okay, so we'll basically, this diagram is not in scale. We'll try to basically locate the reaction which is basically acting on the base. Suppose this is your B. So therefore this will be your B by 2, and your reaction, which is basically acting on the base, that is at a distance of x bar. Okay, so therefore this is the eccentricity at which the resultant reaction is basically acting on the base of the wall. So this is your R. This is your R. Are you getting my point? So this is the center of the footing, the retaining wall base. This is the location of the resultant reaction at the base, which is basically acting at a distance of x bar from the toe of the wall, and this is the eccentricity of the resultant reaction with respect to the center of the base of the wall. Okay, now how we can determine this x bar? So x bar we can determine by taking the moment above the toe of all the forces. Now if you do that, then this will be the final expression will be summation of MR minus summation of MO divided by summation of FB. And we have calculated all the components already. So this is the summation of FB, that is the total vertical forces. This is the total resisting moment, and this is the total overturning moment. Okay, so now it becomes very easy to calculate the x bar, and please keep in mind that x bar is basically calculated from the toe of the wall. So summation of FR this is basically 304.3, and summation of MO, that is overturning moment, 105.02, and summation of FB this is 184.67. So if you calculate 304.3 minus 105.02 divided by 184.67, so this will give you the x bar value 1.08 meter. Now what is the B by 2 distance? Now what is the total width of the first? Let me calculate the total width of the base of the wall. So the total width, the width B, this is basically 3 meter. Na? 0.65, 0.7 plus 0.3 plus 0.7 plus 0.65. So this total width, this is basically 3 meters. Okay. So therefore, this B by 2, this is 1.5 meter. Now the resultant reaction is basically acting at a distance of 1.0 meter. So therefore, what is the eccentricity? So eccentricity would be B by 2 minus x bar. So B by 2 is your 1.5 minus 1.08. So that means 0.42. Now, does this eccentricity create any tension at the base? What is the criteria to check that condition? So the criteria is this eccentricity should be less than B by 6. Now what is the B value? 3, and this is 6, so therefore 0.5 meter. This is the limiting value for eccentricity, or allowable value for eccentricity. Okay, and we are having a value of 0.42 of the resultant reaction, the eccentricity of the resultant reaction. Okay, so that means it's okay. So there is no tension at the base of the footing. There is no tension at the base of the wall. Okay, that means so we have checked one condition, that is no tension condition. There is no tension at the base of the wall. Now we'll proceed further. We'll check the overturning condition. So factor of safety against overturning. And it, as you know, this is the ratio of summation MR divided by summation MO. So this is 304.3 and this is 105.02. Okay. 304.3 divided by 105.02. That means I am getting a value 2.90 approximately. Okay. So 2.90. So it's basically greater than 1.5. That means okay. So we have basically summarized at the beginning of this problem all the conditions that we need to check. So factor of safety against overturning, factor of safety against sliding, factor of safety against bearing failure, and no tension condition, or check for no tension condition at the base. Okay. So in this way we have checked two conditions. So the conditions for no tension at the base and condition for factor of safety against overturning, and it's basically found out to be greater than 1.5. Now we'll calculate factor of safety against sliding. Now how we can calculate? So we can calculate in this fashion: summation of FB tan delta plus CA B divided by summation of FH. Now summation of FB, that we know, because this is 184 point something, 184.67. Delta. Now what is the delta value in this case? So delta value in this case, it will be basically delta value of the subsoil, not the backfill. Okay. So we are right now checking the sliding condition, factor of safety against sliding. So this delta value we have to basically use. So when we have determined the active earth pressure coefficient, we have basically considered the delta value of the backfill material. However, when we will check for the factor of safety against sliding, we should use the delta value of the subsoil. Now what is the delta value of the subsoil? It is 0.75 times 25. That means 18.75 D. Okay. So this would be 184.67, or let me write it here, 184.67 into tan of 18.75 plus, now what is the addition at the base? So addition, I think it's mentioned as the addition factor as 0.9. So the addition would be this factor multiplied by the cohesion of the subsoil. So now the cohesion of the subsoil is basically 15 kPa. That means 0.9 times 15, that will give you the addition at the base. So 0.9 multiplied by 15. And what is the B value? So B value is your 3. Okay. One point to be noted here, that we are basically taking the full width here. Okay, considering full width. So due to eccentricity, there is a concept of modified width that also you can utilize there. However, here we are basically considering the full width. Full width means 3. And what are the total horizontal forces in this system? This is nothing but the horizontal component of this PA. So that means 63.01. 63.01. So tan of 18.75 multiplied by 184.67 plus 0.9 multiplied by 15 multiplied by 3 divided by 63.01. So it will give you, I hope, 1.64. Okay, so that means greater than 1.64. It's also okay. Okay, now we'll check for the last condition, that is the factor of safety against bearing. Okay, and this is Q nu divided by summation of FP, and Q nu, this is the net ultimate bearing capacity. Here we will use the concept of modified width. Okay, so B prime divided by, or FB, that you know. Now what is the Q nu? Okay, first let me write the expression for B prime. So it will be B minus YC. Okay, you can also consider EX, eccentricity in the one direction. So therefore 3 minus 2 into 0.42 that means 2.16 meter. And what is the QNU? So QNU, this is basically QU minus gamma df. And what is the value of QU? So QU, this is C, NC, SC, DC, IC plus gamma df, SQ, DQ, IQ plus 0.5 gamma B, N gamma, S gamma, T gamma, I gamma. Okay, so this is the expression for ultimate bearing capacity, and we are considering Meyerhoff's theory. Okay, though you can go for any other theories also which are available to calculate the net ultimate bearing capacity of a footing. Okay, now we'll try to summarize the parameters which are involved in this expression one by one. So B prime already we have calculated 2.16 meter. This FB that we have determined already as 184.67. Now what are these C, gamma, DF? So C value, this is the again the value of subsoil, cohesion value of subsoil 15 kPa. Gamma is your 17 kilonewton per meter cube, and phi is your 25 degree. So the shear strength parameters, C, this is your 15 kPa and phi equals to 25 degree, obviously for subsoil, and gamma is your 17 per meter cube. And one more thing, what is the depth of the foundation? Means depth of the base. So this is basically 0.5 plus 0.5. So summation of these two values, 0.5 plus 0.5. So df, this is 0.5 plus 0.5, that is 1 meter. Okay, again I am writing here as well. So df is your 1 meter. Okay. Now corresponding to this phi equals to 25 degree, we'll first determine the bearing capacity factors. So this row, so this table will basically give you the bearing capacity factors based on Meyerhoff's theory. Okay. So this row, phi corresponding to phi equals to 25 degree, you will get the NC value, NQ value, and the N gamma value. So NC is your 20.7, then NQ is your 10.7, and N gamma is your 6.8. Okay, so these are the bearing capacity factors. So C, NC, gamma, DF, gamma, B, these are already known. Okay, again this B value you should consider B prime, since we are considering the eccentricity of the loading, and this value as well. Okay, one parameter I have missed here. So gamma, DF, NQ will be there. Okay, so NQ and N gamma also we have known. Now we will determine the shape factors SC, SQ and S gamma. So for that we will take the help of this table. So SC, SQ and S gamma. Now what is the value of SC? So SC value is 1 plus 0.2 Kp B by L. Now what is Kp? Kp value is nothing but tan square 45 degree plus phi by 2. Now in this case your phi value is basically 25. So phi equals to 25. So Kp would be tan of 45 plus 12.5. So that means 2.46. Okay. So 2.46, that would be your Kp. Okay. And all the expression will basically consider B prime value instead of B, because we are having the eccentricity of the resultant load. Okay. So therefore this SC, this will be 1 plus 0.2 into 2.46 into 2.16 divided by L. L is your infinity. Why? Because this is basically the length already we have considered, that this is basically we are considering one unit strip along the perpendicular to this presentation slide. So therefore this is basically a strip kind of footing. So therefore this SC, SQ, S gamma, this will become basically 1. So SQ, SC, SQ, S gamma, this will basically become 1. Now coming to DC, so this will be 1 plus 0.2, Kp is your 2.46, DF is your 1, and B prime is basically 2.16. Okay, so this would be basically B prime. So 1.14 I am getting. Now dq d gamma, this will be equal, and it will be 1 plus 0.1 root 2 root under 2.46, 1 divided by. So 1.07 the value for dq d gamma. Okay, now the next factors are IC, IQ. So IC, IQ, I gamma. So IC and IQ both are equal, and it's having a value of 1 minus. Okay, this alpha parameter you may confuse this alpha with the backface angle. So here I am basically introducing a separate variable called psi, okay, to distinguish between alpha and psi. So alpha earlier we have used for the inclination of the backface of the wall. Now here the psi is basically the inclination of the resultant load with the vertical on the or at the base of the footing. Okay, so this is psi. So this is basically 1 minus psi by 90. Now what is the value of psi? So this psi value you can calculate it from tan inverse summation of fh divided by fp. That means tan inverse 63.01 divided by 184.7. So this will give you the value of 18.84 degree. Okay, so 18.84 divided by 19 square. So 0.625, this is the inclination factors for IC and IQ. Then I gamma, so this will be 1 minus psi by 5, 18.84 divided by 25. So 0. 0.05 something I am getting. Okay. What is the value of pi? Yeah, pi is your 25 degree. So 18.84 divided by 25, then 1 minus answer square. Oh, sorry, 0.06. This value is basically 0.06. Okay. Okay, so in this way we have got all the factors which are required to calculate the ultimate bearing capacity first, and then the net ultimate bearing capacity, and finally the net ultimate load, and subsequently the factor of safety against bearing. Okay, so it's very easy to calculate the ultimate bearing capacity. Then just you have to substitute all these values. So C, this is your 15, NC, this is your 20.7, then SC 1, then DC, this is your 1.14, then IC, this is your 0.625. Okay, next gamma DF, gamma is your 17, DF is your 1, then NQ, NQ value is your 10.7, then SQ1, DQ is your 1.07, then IQ 0.5, and finally 0.5 gamma 17, B prime is your 2.16, N gamma 6.8, S gamma 1, D gamma 1.07, and I gamma is your 2.06. Okay, so please calculate. So I am getting something 350.89 or 351 kilonewton per meter square. Okay, so I don't know whether I am getting the correct value or not, because just let me check it once. Okay, so 15 into 20.7 into 1.14 into 0.625. So this value is your 221.23 and 17 into 10.7 into 1.07 into 0.65. This value is your 120.65 and 5 into 17 into 0.16 into 6.8 into 0.06. So this value is your 8 and 0.2. Yeah, something 351 value I am getting. Okay, so therefore QNU, this will be 351 minus 17, that is 334 kilonewton per meter square. Okay, so I think I did a mistake. I don't know whether CNC, SC, DC, IC, gamma, DF, N. Okay, these factors are correct or not? 10.7, gamma, DF, DQ, SQ, DQ, IQ, 0.5 gamma, B, N gamma, S gamma, D gamma, I gamma. Okay, so please check this value. Okay, so I may be wrong for the calculation part. Okay, so please check this calculation. However, the approach should be same. So 334, so therefore the QNU value, this would be 334 multiplied by the 2.16, that is B prime. Okay, so 721.4 kilonewton. So therefore factor of safety against bearing, this will be 721.44 divided by this is your 184.67, that is summation of FP. Okay, so 3.91 getting, and it's greater than 2.5. So that means okay. So in this way all the design checks are performed, and it has been found that the given gravity retaining wall is basically safe, okay, against all these checks. That is factor of safety against overturning, factor of safety against sliding, factor of safety against bearing, and check for no tension condition at the base of the wall. Okay, so please cross check these values whether I am correct or not, because I am getting a slightly different value as I computed earlier. So I cannot figure out at this moment what is the mistake here. So I may be wrong in the calculation part. Okay, so that you please check. Or just before going into the next problem, just let me recalculate it once. All the values I have substituted correctly or not. Okay, so what I can understand from the calculation, that this gamma value, earlier I considered it as 20, because this gamma, oh no, not this gamma, this gamma. So these materials, na, this the subsoil means these materials also are basically assuming the same properties, that is gamma is equals to 17 kilonewton per meter cube, because the first gamma TF component, okay, so this gamma DF component, this represents the surcharge at the base of the base level of the wall. Okay, so this surcharge component, now this surcharge component you can get by multiplying the unit weight of this portion, divide multiplied by multiplication of this unit weight of this portion and the depth of the wall, okay, depth of this embedment. So therefore this value is basically assumed to be same as that of the subsoil, okay, 17 kilonewton per meter cube. So that's why earlier I basically take it as 20, so that's why I am getting a different value. Okay, now it's fine. Okay, so any problem so far? Do you have any problem? Okay, so I am assuming that it's fine. Okay, now we'll move on to this problem 2, that is related to a cantilever seed pile which supports a cohesionless soil of height 6 meter. The water table is at a depth of 2 meter from the ground level. So we have to calculate the distance between the dredge line and the point of zero pressure just below the dredge level. Now, you know what is the dredge level? That this is called the dredge level. Okay, so this is the dredge level. And this is the surface, ground surface. So these are the properties of the cohesionless soil, that above the water table the friction angle 35 degree and the saturated unit weight is 18 kilonewton per meter cube, whereas below the water table obviously the submerged unit weight will come into picture, and the submerged unit weight is 8 kilonewton per meter cube. It's directly given to us. Otherwise you can calculate it by subtracting the unit weight of water from the saturated unit weight of the soil, that is 18 minus 10, 8 kilonewton per meter cube. Now what you have to determine? You have to determine the distance between the dredge line and the point of zero pressure just below the dredge level. Okay, so for that you first need to know the net earth pressure diagram. Otherwise you cannot determine the location of this point of zero pressure. Okay, okay, so in this seed pile problem, rotation of this wall is basically assumed in this fashion. Okay, so in this fashion a rotation the wall is basically assumed. That is, it's basically rotating about this point below the dredge level. Okay, now depending on this reflected pattern of the sheet wall, we can basically divide the soil mass into 4 divisions, that is this part above the dredge level. So this is your dredge level, or we can say DL. So this is division 1, this is 2, this is 3, and this is 4. Okay. So these three components, okay, sorry. Into these four divisions, we can basically divide the entire soil mass depending on the deflected pattern of the sheet wall. Now, among these four divisions, four parts, this part 1 and part 3, it will be under active state. Why? Because in this portion, the retaining wall is basically moving away from the backfill. So in this direction and in these directions, okay. So it's basically moving away from the backfill, this wall, sheet pile wall. And for part 2 and part 4, it will be under passive state, because the wall in this portion is moving towards the backfill. As you can see, in 2 it's basically moving towards the backfill, and 4 also it's moving towards the backfill. So therefore, in these two regions, region 2 and region 4, it will be under passive state, whereas region 1 and region 3, it will be under active state. Okay. So depending on that, we'll have to basically draw the net earth pressure diagram. So net earth pressure diagram, to draw the net earth pressure diagram, so this is the dredge level, and this is your the point of rotation, the level of point of rotation. Okay. Now, since this region 1 and above the dredge level, it is under completely active state. So therefore, the distribution will basically start from something like this. Okay. So we'll basically start one by one. So for that, first we'll determine the coefficient of active earth pressure, and it is 1 minus sine 35 divided by 1 plus sine 35, that is 0.271, and Kp, this is the reciprocal of 0.271, that is 3.69. Okay. So these are the active and passive earth pressure coefficient values. Now, up to this dredge level, since this region 1 is completely under active state, up to this dredge level, means above this dredge level, this region 1 is completely under active state, and there is no soil. This is the void region. Okay, so this is the void region. So therefore, the net earth pressure will be simply the active earth pressure acting on this region. Okay. Now, how we can calculate this active earth pressure in this region? So it will basically start from 0. So since this is the cohesionless soil, so the active earth pressure variation, so here I can write PA Z, this is KA gamma Z, and PPZ, this is KP gamma Z. So these are the variation of active and passive earth pressure with Z. Now Z being measured from this level and again this level. Okay, so when we'll basically move, or we'll basically go down the dredge level, below the dredge level, then in that case, for this portion, we'll basically have to consider Z from this line, because in this portion there is no soil. This is the void part. Okay. So this is the variation of PA and PP with Z. for the active earth pressure and the passive earth pressure distribution. So therefore, this active earth pressure will basically start from a value of 0 and it will basically go up to a value of gamma sat multiplied to up to the water level. Okay, below water table there will be a separate variation. Okay, so up to the water table this value would be gamma sat multiplied by 2. Okay, so that means 18 multiplied by 2. So 18 multiplied by 2, this value you will get 36. Okay, now if this value is 36, then as soon as you encounter the water table, this 36 will remain constant and you will be having the active earth pressure at this dredge level as 18. Okay, sorry, I did a mistake here, please correct me. So this is basically the gamma z. Okay, you have to basically multiply it with k. Now what is the value of k? This is 0.27. 0.27 into gamma z. Gamma is your 18 multiplied by 2. That means 9.72. Now coming to the dredge level, so it will be 18 multiplied by 2 plus 8 multiplied by 8 multiplied by the remaining height. That means 8 multiplied by 4. Okay, so this is your 0, or we can say this is your 2 meter and this is your 4 meter. So therefore the overburden at this level, the dredge level, it will be 18 multiplied by 2 for this portion and then 8 multiplied by 4 for this portion, because now you have basically encountered the water table. This is the water table location multiplied by the coefficient of earth pressure, that is 0.27. So therefore this value would be 18 multiplied by 2 plus 8 multiplied by 4 into 0.27. This value is your 18.36. Okay, and all are in kp. Okay, this we are determining the net earth pressure diagram. Now up to this dredge level it's fine, because the active earth pressure whatever you are getting for region 1, that will be the net pressure, because in this void region you are not having any pressure to counterbalance this active earth pressure. Now as soon as you will basically go down below the dredge level, so in this side you will be having active pressure and in this side you will be having passive pressure. So in this side you will be having active A and in this side you will be having passive P. Now, since the passive pressure coefficient is much greater than the active earth pressure coefficient, that is Kp is much higher than Ka, so the net earth pressure distribution diagram will shift from the right side to the left side. So from this side to this side it will basically shift. Okay, why? Because now your Kp is much greater than K. So up to or above the dredge level in region 1, above the dredge level in region 1, active earth pressure is the net earth pressure. So net earth pressure is basically equal to the active earth pressure, whatever you are getting for region 1 above the dredge level. Since this part is basically void, so it will not exert any pressure, and water pressure from this side will basically balance each other. So from this side and from this side, the water pressure will basically nullify each other. So therefore, since this side is void, there is no soil, so the active earth pressure, whatever you are getting for region 1 above the dredge level, that will be the net pressure above dredge level for region 1. But as soon as you basically come below the dredge level, so one side, this side you are having for region 1 active earth pressure, but this side for region 2 you are having passive earth pressure. Now the difference between these two pressure you have to consider, and that will basically govern the net pressure diagram, net pressure on the wall. Now we have to basically judge which pressure is greater. So we are basically based on the logic that Kp, since the earth pressure coefficient for passive condition is basically much higher than the earth pressure coefficient in active condition, so therefore the net pressure diagram will basically shift from right side to the left side of the wall. So you will be basically having the passive earth pressure diagram like this, and if you basically extend the active earth pressure diagram, so it will be having like this. Now these values, okay, so this is not basically drawn in exact scale, so this value will basically less as compared to this value. So therefore this diagram will basically shift to the left side of the wall. Okay, and we will basically determine that value. So something like this will basically get. Therefore there is a shift in the distribution from right side to the left side, and this is the point of zero pressure. Here the net pressure is exactly 0, and what is the distance, what is the location of this net zero pressure? So from the dredge level we are basically introducing a variable called A prime. So A prime indicates the distance between the dredge level from the dredge level to the net zero pressure location. So A prime basically denotes the location of net zero pressure below the dredge level. Okay, so okay, so up to the rotation part, the level of rotation, the net pressure diagram is fine. Okay, it's okay. Now we'll move further. Now we'll consider region 3 and region 4. So in region 3 you are having active condition, so it's the reverse case here, and for region 4 you are having the passive condition. Okay, so it's the reverse case, and again since Kp is much higher than K, so the net distribution again will basically shift from which side to which side? Now it will shift from left side of the wall to the right side of the wall. Okay, so again you will basically get a point of zero pressure. Is it clear how we are basically getting this type of net earth pressure diagram? So this is qualitative. Okay, so below the dredge level, whatever I have drawn, this is a qualitative diagram, not the quantitative, because we till now I didn't show or didn't write any value for this part, okay, below the dredge level part. And though it's not needed, at least for this problem, okay. Okay, so now how we can determine this A prime? So A prime we can determine, so first we have to consider the active earth pressure from region 1. So we'll have to consider basically the active earth pressure from region 1 and passive earth pressure from region 2. Then we have to at the level of A prime from the dredge level. Okay, so at a distance of A prime from the dredge level, we have to basically calculate the active earth pressure from region 1 and passive earth pressure from region 2, and then we have to basically take the difference between these two, that is passive minus active, and that we have to basically equate to 0. Only the in that condition we can get the value of A prime. Okay, so we'll basically do that part. So okay, before that, let me rename this point. Okay, so this is your O, this is your B, this is your C, this is your D, this is your E, F, G, H, this is your I. Okay, so in this way I have marked all the points. Okay, now we are basically calculating the active earth pressure at point A. So at a distance A prime from DL, this passive earth pressure, the active earth pressure in zone 1, so this will be gamma H into Ka plus gamma A and K. Okay, so okay, instead of this we can basically substitute the values as well. So we are basically determining the active earth pressure for region 1. So for region 1 active earth pressure at this level, it will be the overburden up to that level multiplied by the active earth pressure coefficient. So overburden is your basically 0.27 into 18 multiplied by 2 up to the water level. Then below water level it will be 8 multiplied by 4 up to this dredge level, and then A prime multiplied by 8. Okay, so 18 multiplied by 2 plus 8 multiplied by 4 plus 8 multiplied by A prime. So this is the total overburden, effective overburden up to at a level, at this level, which is basically located at a distance of A prime from the dredge level, and this multiplied by Ka, so that will give you the Pa for region 1, and Pp for region 2, so that you can get simply 8 multiplied by A prime multiplied by Kp. Okay, why 8? Because this is submerged, totally submerged under water table. So, and this part is void, so the distribution will basically start from in this fashion. Okay, so that means 8, this is the submerged unit weight, multiplied by A prime, this is the depth, and this is the Kp. Now this Pp2 minus A1 should be 0. Determine the value of A prime. So therefore, this value 18 multiplied by 2 plus 8 multiplied by 4, 36. 36 plus 32, that means 68. Okay, first 8 multiplied by 3.69 A prime. Okay, just let me simplify here itself. 68. Okay, K value is your basically 0.27. So 68 into 0.27. Therefore 18.36 plus 0.27 A prime. Here 29.52 into A prime. 29.52 into A prime is 0. Okay, so 29.52 minus 0.27, that means 29.5 A prime equals to 18.36, or A prime equals to 0.63 meter. This value is 0. So in this way, we have determined the point of zero pressure, the location of point of zero pressure. So just okay, so in rounding of these values, there may be a mistake. Okay, so it's fine. So 0.63 meter. So this value we have got. So this value we have got now, A prime 0.63 meter. Okay, so it will be a better practice to always put the values at the final stage. Okay, so in the final stage, if you put all the values, so if you, then you will basically have a different value, slightly different value. How that I am showing here, that this PAI and this PP, now the difference between these two, because here also I am rounding off and here also I am rounding off, so this value will be slightly modified as compared to the actual value. Okay, so otherwise it's fine. So in this way you can basically determine the value of A prime, or you can determine from the fundamental equation that PA, so this value if you denote, so if you denote this value as PA, so it will be PA plus gamma prime A prime multiplied by Ka. So this is basically your PA for region 1. Okay, so I am not denoting any variable here. So this is the active earth pressure in region 1 from this side. Okay, so this value we are denoting PA means this value 18.36, and this value from this side, this value will be gamma prime A prime into Kp, the passive earth pressure from this side. Okay, so from this side it will be A prime multiplied by gamma multiplied by Kp, so that will give you the distribution. So it should be 0. Now if this should 0, then A prime Kp minus Ka into gamma prime, it should be equated to Pa. A prime, this value would be Pa divided by gamma prime P minus K. So you may be familiar with this type of expression. Okay, so if you can remember only 3 values, that is Pa, Kp, Ka and gamma prime, then also in this way also you can basically calculate the A prime value, though the approach is same. So earlier we have basically substituted the values from the beginning, but here we basically proceed with the variables, means with this in the symbolic form. We have basically moved to get the final expression in analytical form. Okay, so this Pa value is nothing but 18.36, because you know what is the active earth pressure value at the dredge level from region 1. So this value is 18.36. You know the gamma prime value. Gamma prime means the unit weight of the submerged unit weight of the soil, that is 8, and you know the Kp value, that is 3.69, and you know the Ka value, that is 0.27. Now if you basically calculate, you will be having the same answer. Okay, so something 0.67 meter. So that's why I told you earlier that in this case we have basically got some value 0.63, because we have basically put the values from the beginning and we rounded up each value, and that's why we are getting 0.63, but here we are getting slightly higher value 0.67. So if you instead of, if you basically calculate in this fashion, so because it may create confusion, so instead it's better in this form to write. So this is your gamma H plus gamma A prime, and this is gamma prime. Okay, now this gamma H will be two component. So H in the sense your this side. Now this gamma H, it will be having basically two component. One is your gamma prime, sorry, gamma sat up to a height of 2 meter, up to a depth of 2 meter, that is 2 multiplied by, sorry, 18 multiplied by 2 plus 8 multiplied by 4, and this is also 8. Okay, so let me put it in this fashion only. And if you basically calculate, okay, so you don't round up at earlier, so in the final stage you calculate, and you will basically, you will end up with this value that will be 0.7 meter. Okay, otherwise, since you will be given 4 options, so out of these 4 options also you can easily figure out what should be the correct answer. So there might be some there may be some discrepancy because due to the rounding off, otherwise it's fine. So any problems?
No, sir.
So fundamental is that you have to basically equate the passive earth pressure from region 2 and the active earth pressure from region 1, or you have to basically, you can basically take the difference between 2 and you can equate that difference to 0. Okay, so in that way you can basically get the value of A prime, that is the point of zero pressure from between the ridge line and the point of zero pressure, that is the distance called A prime. So now we'll consider the next problem. Okay, so this is the last problem, and then we'll take one homework problem. So it's a very simple and straightforward problem, and it's connected with problem 2. So here we have to basically calculate the distance between the point of zero pressure and the point of application of the total active pressure for the above retaining wall. Okay, not above retaining wall, it will be removed. So for the retaining wall from problem 2. Okay, so this distance you have to calculate now. Suppose this is the resultant, capital PA, and this is the point of zero pressure. So this height y bar, that you have to figure out, or you have to calculate. Now how you can calculate this y bar? It's very simple. So you have to basically split this diagram, okay, this diagram, this is the active earth pressure diagram. Sorry, not active earth pressure diagram, this is the net pressure diagram above this point of zero pressure, and the resultant of this diagram will basically give you the value of PA. So you should know what is the physical significance of PA. So PA, this is the resultant of this diagram, okay, which I have basically marked twice. So up to this part, up to the point of zero pressure. Now at which level this PA is basically acting, the line of action of this PA from the point of zero pressure, that is basically represented by y bar, and this y bar you have to basically report in problem 3. Now how we can determine this y bar? It's very simple. Just you have to basically take the moment of this diagram about this point of zero pressure. Now if we take the moment, then this PA into y bar, this will be simply equated to the individual force component multiplied by the individual lever arm. Now this individual force and individual lever arm you have to basically calculate. So suppose we are taking, this is one component, this is two component, okay, component 2, then this is 3, and this is 4. So we have basically divided this diagram into 4 basic geometries, okay, regular geometries, that is rectangle and triangle. Though we can basically combine this 2 and 3, and we can basically take a trapezium also, okay. So though we are not doing that. So 1, 2 and 3, 1, 2, 3 and 4, all these 4 components, now we have to basically calculate the forces one by one and the corresponding lever arm from this point of zero pressure. So then you will get this small PAI into YI bar. Therefore, this Y bar, it should be summation of PAI YI bar divided by the total PA. Okay. Now here we'll calculate one by one. 1, 2, 3, 4. So this is your PAI, kilonewton per meter, and this is your YI bar in meter. Please keep in mind that this YI bar is basically calculated from the point of zero pressure. Okay. Now for triangle 1, so it will be half multiplied by this height and this base. This base value is nothing but 9.72. So half 2 into 9.72. Then coming to component 2, it's a rectangle, so that means 9.72 multiplied by 4. So 9.72 multiplied by 4. Then coming to triangle, which is marked as 3, so it will be, this total is basically 18.36. Okay, now out of this 18.36, this part is 9.72. So remaining part is your 18.36 minus 9.72 multiplied by 4 multiplied by half. So half multiplied by 4 multiplied by 18.36 minus 9.72. And finally, the lower triangle, that is the base is your 18.36 multiplied by this A prime. A prime is value is your 0.67 multiplied by half. Okay, so half 0.67 multiplied by 18.36. Okay, now the lever arm value will calculate. So for the top triangle, that is 1, so its CG is basically at a height of 2 by 3 from this side, from this level, from the water table, 2 by 3. So 2 by 3 plus 4 plus 0.67. So 2 by 3 plus 4 plus 0.67. Now coming to rectangle 2, so this will be simply 4 by 2 plus 0.67. 4 by 2 plus 0.67. And triangle 3, it will be 4 by 3. So from this side it's 4 by 3 plus 0.67. 4 by 3 plus 0.67. And finally for the lower triangle, that is triangle 4, So it will be from this side, that is from the apex of this triangle. So 2a prime by 3, that is 2 into 0.67 by 3, 2 into 0.67 by 3. Okay, so if you calculate these values, so first value will be 9.72, then 9.72 multiplied by 4, that means 38.88, then 18.36 minus 9.72 into 2, that is 17.28, and then 18.36 into 0.67 divided by 2, that means 6.15, and these values are 5.34, 2.67, 2, and this is 0.45. Now you can substitute these values here. So 9.72 multiplied by 5.34 plus 38.88 multiplied by 2.67 plus 17.28 multiplied by 2 plus 6.15 multiplied by 0.45 divided by 9.72 plus 38.88 plus 17.28 plus 6.15. Okay, so please calculate. So 2.68, this is the answer. So therefore this distance, this lever arm, this value is your 2.68 meter. Okay, so still now we don't know what are the values of this part. This part we did not determine, and it was not required to solve at least problem 2 and problem 3. Now this part will come into picture when we will go for to determine the depth of this wall, the depth of embedment of this wall. Okay, so please take this part as a homework. So, determine the required depth of embedment of the wall. Okay, so basically it is the standard practice that whatever value you will basically get after the calculation, you should increase that value by 20 to 30 or 40%. Okay, so I am basically giving you the value that you should increase it by 20%. So whatever value you will basically get from the calculation, actual calculation, so that value we should multiply with 1.2. That should be the provided value. Okay, so we are basically taking some margin, safety margin. So suppose you are getting the value as 2 meter from the calculation, but we will provide 2 multiplied by 1.2. So this value 2.4 meter we will provide. So that's why this is the homework. So you please calculate the required depth of embedment for the wall, and then you will basically provide 20% greater value compared to the actual value or the required value. Okay, so this is one homework. And next homework which I selected earlier, so this is regarding the net earth pressure diagram for this given sheet pile but in cohesive soil. So earlier we have basically determined the, no, we didn't determine the net earth pressure diagram fully, but we have learned what should be the qualitative distribution of the net pressure for a cantilever sheet pile in cohesionless soil, purely cohesionless soil. However, in this problem, so this is a pure clay. So in this case, we have to basically determine the net earth pressure diagram for this sheet pile. Okay, so we'll stop here, and I'll request all of you that you please at least try, and if you face any difficulties, then we can discuss about those problems in the next discussion hour. Okay, so that is on 15th October at 5 p.m. So regarding today's session, if you have any difficulties, please let me know. Otherwise, I will end this session here. And thanks a lot for joining this session.